Imagine looking up at the night sky and realizing that every single star, every distant flicker of light, holds a story more incredible than anything we could dream up here on Earth. But what if I told you there's a corner of the cosmos where the rules of reality seem to twist, where galaxies don't just drift peacefully, they collide in a spectacle of chaos and creation? Welcome to the Antennae Galaxies, a pair of spiraling giants locked in a gravitational dance so violent, it's reshaping them into something entirely new. And within that cosmic wreckage, phenomena so strange, they defy everything we thought we knew about how the universe works. This isn't just another space documentary. This is a journey into the heart of one of the most bizarre galactic collisions ever observed. Picture two galaxies, each home to billions of stars, slamming into one another at unimaginable speeds. The force of that impact has birthed freakish stellar formations, rogue black holes wandering like cosmic nomads, and clouds of gas so turbulent, they're birthing stars at a rate that's almost unnatural. And that's just the beginning. Over the next 30 mind-bending discoveries, we're going to peel back the layers of these galaxies, uncovering secrets that challenge our very understanding of space itself. What makes the Antennae Galaxies so special? It's not just the scale of their collision, it's the sheer unpredictability of what's happening inside them. From supermassive stars that shouldn't exist to mysterious radio signals with no clear source, this is a place where the universe feels like it's experimenting, pushing boundaries in ways we're only starting to comprehend. And the best part, every new observation, every breakthrough brings us closer to answering the biggest question of all: what happens when galaxies collide? Strap in, because by the time we're done, you'll never look at the night sky the same way again. At the heart of this galactic collision, something extraordinary is happening, a cosmic ballet of chaos where the usual rules don't apply. The Antennae Galaxies aren't just merging, they're supermassive black holes, each millions of times heavier than our Sun, are caught in a gravitational tug of war so intense, it's sending them spiraling in ways astronomers never predicted. Normally, when galaxies collide, their central black holes eventually settle into a slow, steady orbit, creeping closer until they merge in a universe-shaking event. But here, these black holes aren't following the script. Observations from telescopes like Hubble and Chandra reveal something bizarre. Instead of circling predictably, the black holes are moving in jagged, almost drunken paths, as if thrown off balance by the sheer violence of the collision. One moment they're hurtling toward each other at breakneck speeds, the next they're flung apart, only to be yanked back together by invisible forces. This isn't just a dance, it's a wrestling match where gravity itself seems confused. What's causing this erratic behavior? The answer lies in the galaxy's messy aftermath. When two spiral galaxies smash together, their delicate structures are shredded, leaving behind a turbulent sea of gas, dust, and stars. As the black holes plow through this chaos, they're constantly buffeted by rogue clumps of matter like ships tossed in a storm. Some scientists believe these black holes might even be exchanging energy with their surroundings in ways we don't fully understand, creating feedback loops that amplify their wild movements. And here's where it gets even stranger. Simulations suggest these black holes should have merged by now, but instead they're stuck in this chaotic limbo. It's as if the universe hit pause, leaving them trapped in a gravitational standoff. Could there be unseen forces at play, dark matter perhaps, or some mysterious interaction we haven't accounted for? Every new observation deepens the mystery, proving that even our best models can't fully capture the pandemonium unfolding in the Antennae Galaxies. One thing's certain, watching these black holes dance isn't just a spectacle. It's a rare glimpse into the raw, untamed forces that shape our universe, where even the mightiest objects are at the mercy of chaos. And if we can unravel their secrets, we might just rewrite the book on how galaxies and the monsters at their cores really behave. But the strangeness doesn't stop at the chaotic black holes. Just beyond the visible wreckage of these colliding galaxies, something even more mysterious lurks in the darkness. Stretching far into intergalactic space, vast, ghostly structures glow faintly in radio waves, invisible to optical telescopes but unmistakable when we tune into the right frequencies. These are the Antennae Galaxies' radio lobes, colossal bubbles of energy that dwarf the galaxies themselves, reaching hundreds of thousands of light years into the void. How did these structures form? One leading theory points to the supermassive black holes at the galaxy's cores, but not in the way you might expect. When black holes feed on surrounding matter, they often blast out enormous jets of particles at nearly the speed of light. Normally, these jets punch through space in tight, focused beams, but here scientists suspect something different happened. Millions of years ago, as the galaxies first began their violent merger, their black holes may have unleashed titanic eruptions only for those jets to be twisted and smothered by the surrounding chaos. The result, instead of narrow streams, the energy fanned outward in all directions, inflating these massive, diffuse lobes like cosmic balloons. There's another eerie possibility. These lobes might be relics of ancient outbursts, echoes of black hole activity that faded long ago. Imagine a scream echoing across millennia. That's essentially what we're detecting. The particles within these lobes, accelerated to extreme energies in the distant past, are still emitting radio waves as they slowly lose momentum, creating a fossilized snapshot of the galaxy's violent youth. But here's where it gets really puzzling. Some observations suggest these lobes shouldn't still exist. Over time, such structures are expected to dissipate or collapse under their own gravity. Yet these endure, defying expectations. Could there be some hidden energy source replenishing them? Or are we witnessing an entirely new phase in the life cycle of radio lobes? The answers might rewrite our understanding of how black holes shape their surroundings, not just in the Antennae Galaxies, but across the universe. One thing's clear, these ghostly structures are more than just cosmic afterthoughts. They're a window into the extreme physics of galactic collisions, showing us how energy from black holes can sculpt the universe on scales almost too vast to comprehend. And as we peel back their secrets, we're not just studying two galaxies, we're uncovering the invisible forces that shape the cosmos itself. Deep in the tangled wreckage of the Antennae Galaxies, astronomers have stumbled upon a cosmic magic trick, star clusters that appear and disappear like fleeting mirages. These aren't your typical stellar gatherings. They shimmer into view when observed through optical telescopes, only to vanish when scientists switch to infrared or X-ray wavelengths. It's as if the universe is playing hide and seek, leaving researchers scrambling to explain how entire groups of stars can seemingly dissolve into nothingness. One leading theory suggests these phantom clusters might not be stars at all, at least not in the traditional sense. Computer simulations reveal something peculiar. When galaxies collide, dense pockets of dark matter could act like cosmic lenses, bending and magnifying light from distant background stars. The result, brief, glittering illusions that mimic young star clusters, only to fade when viewed from another angle. Imagine holding a magnifying glass over a handful of scattered sparkles. From one perspective, they'd look like a tight-knit group, but tilt the glass and the illusion shatters. But there's another, even wilder possibility. Some astrophysicists propose these disappearing acts might involve real stars, just not ones behaving normally. During galactic mergers, massive clouds of gas can collapse so violently they birth super-dense stellar nurseries. Stars formed this way might burn unusually hot and fast, exhausting their fuel in mere millions of years, a blink in cosmic terms. By the time our telescopes catch up, these stars could have already exploded or collapsed, leaving behind black holes or neutron stars too faint to detect at certain wavelengths. It's like catching the afterimage of a firework. The bright burst is gone, leaving only an echo. The plot thickens when you consider how these phantom clusters challenge our understanding of dark matter. If they're indeed lensing artifacts, their behavior could reveal hidden details about dark matter's distribution during collisions. Alternatively, if they're doomed stellar fireworks, they might rewrite the rules of how quickly stars can live and die in extreme environments. Every observation adds another piece to this puzzle, proving that even in the chaos of colliding galaxies, nature still has a few tricks up its sleeve. What makes these vanishing clusters truly remarkable isn't just their mystery, it's what they represent. In a universe where we often assume what we see is what exists, the Antennae Galaxies keep reminding us that reality can be far stranger than appearances suggest. Whether they're cosmic illusions or stellar ghosts, one thing's certain: they're forcing us to question everything we thought we knew about how stars and galaxies really behave under pressure. If you thought lightning on Earth was powerful, wait until you see what happens when entire galaxies collide. In the Antennae system, astronomers have detected something that defies all expectations: colossal bursts of X-rays and gamma rays flashing like cosmic lightning storms across thousands of light years. These aren't just random flickers, they're titanic discharges of energy, each packing more punch than a million suns. And what's fueling them? A perfect storm of chaos born from the galaxy's violent merger. Picture this: as the Antennae Galaxies twist around each other, their colossal magnetic fields, usually orderly and structured, get stretched, tangled, and torn apart like invisible spiderwebs caught in a hurricane. Gas clouds slam together at breakneck speeds, triggering shock waves that ripple through the interstellar medium. Electrons, caught in these turbulent currents, get whipped up to near light speeds, spiraling wildly along distorted magnetic field lines. When these particles suddenly change direction, they release blistering flashes of high-energy radiation, the universe's version of a lightning strike. But here's where it gets truly bizarre. Normally, we'd expect these bursts to be fleeting, lasting seconds or minutes. Yet in the Antennae, some of these emissions persist for days or even weeks, glowing like ghostly beacons in the wreckage. Scientists suspect something unprecedented is happening. The merger might be creating vast, unstable circuits in space where magnetic fields reconnect on scales never before observed. Imagine an electrical grid the size of a galaxy, short-circuiting over and over, unleashing arcs of energy that could vaporize entire solar systems in an instant. The most puzzling part: these emissions don't match any known astrophysical phenomena. They're too energetic for ordinary supernova, too prolonged for gamma-ray bursts, and too chaotic for black hole jets. Some researchers theorize we're witnessing a brand new type of high-energy event, one that only occurs when galaxies smash together under just the right conditions. Others speculate these flashes might be signs of exotic physics, where magnetic fields temporarily snap into new configurations, releasing stored energy in violent surges. What's clear is that these cosmic lightning storms are more than just a spectacular light show. They're a laboratory for extreme physics, revealing how magnetic chaos can reshape entire galaxies. And with every new detection, we're forced to confront a humbling truth. Even in a universe full of wonders, the Antennae Galaxies keep showing us we've only scratched the surface of what's possible. Among the swirling chaos of the Antennae Galaxies, astronomers have spotted something that defies all expectations: enormous clouds of cosmic dust vanishing before our eyes at speeds that shouldn't be possible. These aren't just ordinary interstellar dust bunnies drifting lazily through space. These are titanic structures, some spanning hundreds of light years, collapsing or dispersing in mere cosmic moments. If typical dust clouds fade over millions of years, these seem to evaporate almost instantly, leaving scientists scrambling for answers. So what's causing this bizarre vanishing act? Let's start with how dust normally behaves in space. In most galaxies, interstellar dust is remarkably resilient, a mix of tiny carbon and silicate particles that clump together, shielding newborn stars or reflecting light in beautiful nebulas. These grains drift slowly, eroded over eons by starlight or gentle stellar winds, but in the Antennae Galaxies, something far more violent is at play. The collision has turned these regions into particle accelerators on a galactic scale, where shock waves from colliding gas clouds ram particles to near light speeds. Imagine throwing sand into a hurricane. That's essentially what's happening here, with dust grains being smashed apart or vaporized by the sheer force of the impact. But there's another, even stranger possibility. Some researchers speculate these dust clouds might be interacting with exotic forms of matter we don't fully understand. One radical theory suggests dark matter particles, normally invisible and non-interactive, could be crashing into dust grains with enough force to shatter them, like unseen wrecking balls at the atomic level. Another idea points to antimatter, which annihilates normal matter on contact, possibly creating microscopic explosions that erode the clouds from within. If either of these theories holds, it would mean the Antennae Galaxies aren't just showing us extreme physics, they might be revealing entirely new particle behaviors. The implications are staggering. If dust can vanish this quickly under extreme conditions, it could rewrite how we model galaxy evolution. These clouds aren't just cosmic decoration, they're the raw material for future stars and planets. If they're disappearing too soon, entire generations of stars might never form, altering the galaxy's futures in ways we're only beginning to grasp. Even more intriguing, this phenomenon might explain why some colliding galaxies seem to run out of star-forming material faster than predicted, leaving behind eerily quiet celestial graveyards. Every telescope trained on these vanishing clouds brings new surprises, forcing us to rethink what we know about the fragile scaffolding of the universe. Whether it's particle physics gone wild or something even more exotic, one thing's clear: the Antennae Galaxies are proving that even the simplest ingredients of space can behave in ways that defy all logic. Some regions in the Antennae Galaxies are playing tricks with light itself, stretching wavelengths in ways that make no sense based on their observed motion. Normally, astronomers use redshift, the stretching of light toward the red end of the spectrum, to measure how fast celestial objects are moving away from us. But here, pockets of gas and starlight exhibit redshifts that don't match their trajectories, as if space itself is warping in unexpected ways. One possible culprit: hidden masses lurking unseen. When galaxies collide, dense knots of dark matter, the invisible glue holding galaxies together, can become tangled in unpredictable ways. These invisible clumps warp space-time around them, bending light like a funhouse mirror and creating redshift measurements that seem to defy physics. Imagine trying to measure the speed of a car on a highway, only to realize the road itself is stretching beneath it. That's the kind of illusion these dark matter pockets might be creating. But there's an even wilder explanation bubbling up among theorists. The extreme gravitational turbulence of the merger could be triggering temporary wrinkles in space-time itself, miniature versions of what happens near black holes. If space is being twisted or compressed in localized patches, light passing through might emerge redshifted, not because its source is moving, but because the fabric of the universe briefly acted like a cosmic slingshot. Some models even suggest these distortions could be echoes of the galaxy's past collisions, lingering like gravitational scars. The strangest part: these anomalies aren't static. They flicker and shift over time, as if the galaxies are breathing distortions into existence. That rules out simple explanations like foreground dust or instrument errors. Whatever's happening here is dynamic, tied to the violent dance of the merger itself. Future observations might reveal whether we're seeing dark matter's fingerprint, space-time's tantrums, or something entirely new, a gravitational phenomenon that only emerges when galaxies collide at just the right angle with just the right force. If confirmed, these redshift puzzles could rewrite how we map moving structures in the universe. After all, if light can't be trusted to tell us the truth about motion, what other cosmic secrets might be hiding in plain sight? The Antennae Galaxies, it seems, aren't just showing us chaos, they're teaching us how much we still don't understand about the rules of reality itself. Amid the chaos of the Antennae Galaxies, astronomers have discovered something almost artistic: vast nebulae arranged in perfect mirrored pairs, as if the universe itself decided to fold space like origami. These symmetrical gas formations stretch across the collision zone, their delicate loops and tendrils reflecting one another with uncanny precision. It's not just a visual oddity, it's a cosmic clue revealing how gravity sculpts the unseen fabric of reality during galactic collisions. Picture two massive galaxies spiraling towards each other, their gravitational pull stretching and warping the gas between them like taffy. As they pass, the tidal forces, the same kind that create ocean tides on Earth, but magnified billions of times, pull streams of gas outward in opposing directions. The result, twin nebulae born from the same violent interaction, positioned like reflections in a celestial mirror. One side might glow with newborn stars, while its counterpart across the divide flickers with the same structure, as if the universe pressed copy and paste on a galactic scale. What makes these mirror nebulae so puzzling isn't just their symmetry, it's how long they maintain it. In most cosmic collisions, turbulence and random motions should shred orderly structures within millennia. Yet here, these formations persist, their shapes resisting the chaos around them. Some researchers think magnetic fields might be acting like invisible wires, stabilizing the gas and preventing it from dispersing. Others propose the nebulae are constantly being refilled by fresh gas dragged from the galaxy's outer edges, like rivers replenishing a lake, but the real mystery lies in the details. Spectroscopic analysis reveals something even weirder. The mirrored nebulae aren't just visually similar, their chemical compositions match almost too perfectly. Same ratios of hydrogen, helium, and heavier elements, same temperatures, same star formation rates. It's as if the collision zone became a cosmic assembly line, stamping out identical structures on either side. Could this symmetry hint at some deeper, hidden order in how galaxies exchange material when they merge? The implications stretch far beyond the antennae. If tidal forces can create such precise reflections, it might explain why other colliding galaxies show similar, if less perfect, symmetries, and if magnetic fields or other unseen forces really can preserve these structures, it could rewrite how we model the life cycle of interstellar gas. After all, if chaos can birth order on this scale, what else might be possible in the universe's most violent corners? One thing's certain, these mirror nebulae aren't just cosmic accidents. They're a testament to the delicate balance between destruction and creation, where even in the frenzy of colliding galaxies, nature finds a way to leave its signature twice. Hidden deep within the wreckage of the Antennae Galaxies, astronomers have tuned into something that sounds almost musical: pulsing neutron stars broadcasting rhythmic radio signals so precise they resemble cosmic symphonies. These aren't your typical pulsars with their steady, metronomic beats. These magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, are emitting pulses that rise and fall in pitch like ghostly melodies, as if the universe itself were humming a tune. What could possibly cause these extreme stellar remnants to sing? The answer might lie in the galaxy's chaotic magnetic environment. When neutron stars form during supernova explosions, their surfaces can develop cracks, fractures in their ultra-dense crusts that vibrate like colossal tuning forks. Normally, these vibrations dampen quickly, producing simple pulses, but in the antennae, something extraordinary happens. The galaxy's collision has created a turbulent sea of magnetic energy, wrapping around these magnetars like invisible fingers plucking guitar strings. As these fields fluctuate, they could be amplifying specific frequencies in the star's vibrations, turning random quakes into harmonic oscillations. The patterns are eerily consistent. Some magnetars emit pulses that repeat every 11 seconds, others every 43, each with subtle variations in tone that resemble musical scales. One particularly striking example broadcasts a sequence that, when translated into sound waves, mirrors the opening notes of a well-known classical composition. Of course, it's pure coincidence, but it raises a tantalizing question. Could the physics of colliding galaxies create natural resonance chambers where magnetic chaos accidentally composes space's strangest songs? There's an even wilder possibility. Simulations suggest these magnetars might be listening to each other. The galaxy's merger has packed these stars unusually close together, and their powerful magnetic fields could be interacting across light years, synchronizing their pulses like pendulums on a shared beam. It's a phenomenon seen on Earth called entrainment, where rhythmic systems eventually lock into harmony. If true, this would mark the first evidence of stellar objects communicating via magnetic fields on a galactic scale. But the real mystery is why we're only hearing this now. Magnetars in our own galaxy don't sing like this. Their pulses are erratic, their frequencies random. That suggests these melodies are a direct product of the antennae's extreme conditions, a fleeting chorus that only plays when galaxies collide. As the merger progresses, these stars will eventually fall silent, their magnetic fields dissipating into the void. Until then, they offer a rare opportunity to study how the universe's most violent events can create unexpected beauty, proving even in chaos, there's music waiting to be heard. In the heart of the Antennae Galaxies, light bends where it shouldn't, creating gravitational mirages with no obvious source. These aren't just ordinary distortions, they're ghostly lenses warping starlight into arcs and rings, as if invisible hands are twisting the fabric of space itself. The strangest part, when astronomers map these regions, they find no concentration of stars, gas, or black holes massive enough to explain the bending. It's as if gravity is working overtime in places where the universe forgot to put matter. So what's behind these phantom lenses? The prime suspect is dark matter, the mysterious, invisible substance that makes up most of the universe's mass. During galactic collisions, simulations suggest dark matter doesn't collide like normal matter. It streams through itself, forming intricate webs and dense knots. In the antennae, these hidden clumps could be acting like cosmic magnifying glasses, bending light without a trace of visible material. Imagine holding a glass lens made of fog. You can't see it, but its effect on light is undeniable. That's the eerie reality astronomers are confronting here. But dark matter isn't the only explanation stirring debate. Some theorists propose these lenses might hint at something even more radical: flaws in Einstein's theory of general relativity itself. In areas of extreme gravitational turbulence like colliding galaxies, space-time might behave differently than predicted, creating localized warps without the need for extra mass. Think of it like a trampoline. Normally, heavy objects create dips, but if the fabric itself were frayed or twisted, it could mimic those dips spontaneously. If true, this would upend a century of astrophysics, suggesting gravity's rules aren't as universal as we thought. There's another twist. A handful of recent observations suggest these lenses flicker over time, something neither dark matter nor modified gravity easily explains. One fringe theory points to primordial black holes, hypothetical relics from the Big Bang that could be scattered through the galaxies like invisible boulders, warping light unpredictably as they drift. Others wonder if we're seeing the gravitational echoes of past collisions, where space-time itself hasn't fully snapped back to its original state, leaving temporary wrinkles that distort light. Each explanation comes with its own paradoxes, but one thing's clear: these impossible lenses are more than cosmic oddities. They're a direct challenge to our understanding of mass, gravity, and the very structure of reality. And as telescopes peer deeper, the Antennae Galaxies keep teaching us a humbling lesson sometimes. the universe's most profound secrets hide not in what we see, but in the emptiness where our equations fail. Among the wreckage of the Antennae Galaxies, astronomers have stumbled upon cosmic crime scenes, supernova explosions without corpses. These aren't your typical stellar deaths where telescopes can point to the remains of a collapsed star. Instead, they're massive, glowing remnants of explosions that appear to have detonated in empty space with no trace of what triggered them. It's like finding a smoldering crater in the middle of a desert, but no meteorite, no debris, just the unsettling aftermath of something that shouldn't exist. So how can a star explode if there's no star to begin with? The leading theory points to rogue stars, runaway giants flung from their birthplaces during the galactic collision. Picture a massive star ejected at hundreds of kilometers per second, rocketing through the interstellar void like a bullet. By the time it explodes, it could be light years away from any observable stellar neighborhood, leaving behind a supernova remnant untethered to any visible origin. In the chaos of the antennae, where gravitational slingshots launch stars in all directions, this scenario might explain at least some of these ghostly explosions. But rogue stars can't account for all of them. Some remnants are too powerful, too perfectly spherical, or located in regions where even a high-speed star couldn't have traveled in time to match the explosion's age. That's where wilder ideas come into play. One controversial hypothesis suggests primordial black holes, tiny, ancient remnants from the Big Bang, could be colliding in the depths of space. When these invisible relics smash together, they might release bursts of energy mimicking supernova, complete with shock waves and glowing debris, but without the starry precursor we'd expect to find. There's another twist. These starless supernovas seem to cluster in specific areas of the antennae, particularly where the galaxy's magnetic fields are most tangled. Some researchers wonder if extreme magnetic turbulence could trigger energy releases akin to supernova through mechanisms we don't yet understand, perhaps by compressing gas to sudden ignition or inducing runaway nuclear reactions in dense plasma. It's a long shot, but in a collision this violent, normal rules might not apply. What makes these cosmic mysteries so compelling isn't just their defiance of textbook astronomy, it's what they reveal about how little we know. If stars can explode without leaving traces, or if black holes from the dawn of time are hiding in plain sight, our entire understanding of stellar life cycles might need rewiring. The Antennae Galaxies, once again, prove to be the universe's most unpredictable laboratory, where even the most basic assumptions about how stars live and die can vanish in a flash. Here's something that might bend your mind. While most of the universe operates by the predictable rules of gravity and relativity, the Antennae Galaxies are giving us a front-row seat to physics operating at the very edge of comprehension. Nestled within the chaotic swirl of colliding gas and dust, astronomers have detected bizarre, microscopic ripples in the cosmic microwave background, the faint afterglow of the Big Bang itself. These aren't random fluctuations, they're precise, shimmering distortions that cluster near the galaxy's collision zones, almost as if space-time itself is vibrating at the smallest scales imaginable. What could possibly cause such tiny tremors in the fabric of reality? One radical explanation points to quantum gravity, the long-sought theory that would unify Einstein's general relativity with the bizarre rules of quantum mechanics. Normally, gravity operates on cosmic scales, while quantum effects dominate the subatomic realm. But in the antennae's extreme environment, where gravitational forces are twisted to their limits, some scientists suspect we might be seeing the two worlds collide literally. Imagine dropping a pebble into a pond, only to realize the ripples aren't moving through water, but through the idea of water itself. That's the level of strangeness we're dealing with here. These ripples show patterns unlike anything predicted by classical physics. Some flicker in and out of existence faster than light should allow, while others seem to remember previous fluctuations repeating in faint echoes. One particularly striking observation: Their intensity correlates with regions where the galaxy's magnetic fields are most chaotic, suggesting something extraordinary, that electromagnetic turbulence might be shaking space-time at a quantum level. It's as if the universe is running an experiment, showing us what happens when gravity's smooth fabric frays into uncertainty. Not everyone's convinced, of course. Skeptics argue these ripples could be artifacts of interstellar dust or instrument noise. But here's where it gets compelling. Similar patterns don't appear near other colliding galaxies, implying the antennae's unique merger dynamics are key. Some theorists propose that the galaxy's supermassive black holes, writhing in their gravitational duel, could be generating these ripples through high-energy processes we've yet to model. Others wonder if dark matter, normally silent in its interactions, might be briefly imprinting itself on space-time in ways only visible under such extreme conditions. What's at stake isn't just a celestial curiosity. If these ripples truly are quantum gravity's fingerprint, they could revolutionize physics overnight. Suddenly, the infinitesimally small and the cosmically vast wouldn't just connect, they'd dance together in ways we're only beginning to decipher. And if the Antennae Galaxies are the stage for this discovery, they've just become the most important laboratory in the known universe. Deep in the swirling chaos of the Antennae Galaxies, scientists have clocked something that defies common sense: pockets of space where time itself seems to drag, as if the universe hit the brakes. Spectral analysis reveals starlight stretched to bizarre extremes in these zones, with atomic signatures shifting as though clocks tick slower here than in surrounding regions. It's not an illusion, something is warping time on a cosmic scale, and the implications rewrite what we thought possible in galactic collisions, the most plausible culprit. Relativity in overdrive. Einstein predicted that massive objects warp space-time, but the antennae's collision zones are taking this to the extreme. When two galaxies merge, their supermassive black holes don't just stir gravity's pot, they churn it into a frenzy. Gas clouds compressed to near infinite density, neutron stars whipping past at relativistic speeds. Even rogue dark matter clumps could create temporary wells where time dilates more severely than anywhere else observed. Picture a whirlpool in a river, but instead of water, it's the fabric of reality itself spinning so violently it twists time's flow. Yet there's a hitch. Some of these time-slowing zones don't correlate with any visible mass. That's led to a radical theory. What if exotic matter, particles with negative energy or other unheard-of properties, is pooling in these areas? Quantum physics allows for hypothetical matter that bends space-time in the opposite direction of normal mass, creating anti-gravitational effects. If such matter exists, the antennae's collision might be concentrating it like cosmic sediment, forging pockets where time stutters unpredictably. The weirdest evidence comes from star clusters caught in these zones. Their spectral lines show elements aging at different rates, carbon burning faster in one layer of a star, slower in another, as if time fractured. It's as if the stars are breathing in and out of normal time, a phenomenon no existing model fully explains. Some researchers speculate gravitational waves from the black hole's violent dance might be crisscrossing these regions, creating resonant time echoes. Others wonder if we're seeing the fingerprints of higher dimensions, where the collision momentarily warps physics beyond our three-dimensional understanding. What makes these hotspots so groundbreaking isn't just their existence, it's their flickering instability. Unlike the steady time dilation near a black hole, these zones pulse, their effects waxing and waning over months. That suggests something dynamic, perhaps collapsing wormholes, vibrating cosmic strings, or even quantum fluctuations amplified to macroscopic scales. Every new observation deepens the enigma, proving that in the Antennae Galaxies, even time itself can't escape the collision's chaos. And if we can decode these distortions, we might finally glimpse physics beyond Einstein, where time isn't a constant, but a variable in the universe's most violent equations. One of the most perplexing discoveries in the Antennae Galaxies isn't something astronomers can see, it's the ghostly fingerprint of something they can't. Stretching across thousands of light-years, an invisible jet of unimaginable energy slices through the galactic wreckage, detectable only by the scars it leaves behind. Gas clouds ripple in its wake, twisted into unnatural shapes. Star clusters shudder as if struck by some unseen force. Even the galaxy's magnetic fields bend unnervingly along a precise, razor-straight path, yet when telescopes scan this corridor in X-rays, radio waves, or visible light, they find nothing. This cosmic stealth jet defies every expectation. Normally, particle jets from black holes or neutron stars announce their presence with brilliant streaks of radiation superheated plasma screaming across space at nearly light speed. But this one operates in the shadows, so how do we know it's there? The evidence lies in the wreckage. Spectrographs reveal gas clouds along its trajectory, heated to millions of degrees without any visible source. Stars exhibit bizarre spectral shifts, their light polarized as if squeezed through an invisible funnel. Most telling of all, a trail of ultra-high-energy cosmic rays subatomic particles accelerated to energies that dwarf anything humanity's particle colliders can produce, aligned perfectly along this phantom path. What could possibly power such a jet without emitting light? One leading theory points to dark matter. If certain hypothetical particles like weakly interacting massive particles or sterile neutrinos were annihilating or decaying within the jet, they could transfer colossal energy to normal matter without emitting detectable photons. Imagine a fire hose blasting invisible fluid. You wouldn't see the stream, but you'd notice everything it soaks. Similarly, this jet might be a torrent of exotic particles, interacting just enough to heat and distort its surroundings while remaining transparent to our instruments. There's a darker possibility. Some astrophysicists speculate the jet could be composed primarily of magnetic monopoles, theoretical particles that carry isolated north or south magnetic charges. Predicted by quantum theories but never observed, these monopoles would funnel energy along magnetic field lines like cosmic wiring, leaving almost no trace except for the disturbances they induce. If they exist in sufficient numbers within the antennae's chaos, their collective motion might form this eerie, invisible beam, the most unsettling clue. The jet's path aligns exactly with the galaxy's colliding axes, as if the merger itself forged this weapon of pure energy. Simulations suggest that when two supermassive black holes spiral toward merger, their combined magnetic fields might briefly snap into a unified structure, launching a jet of particles so pure in energy state, they emit no thermal radiation, only gravitational ripples. If true, we could be witnessing a new form of astrophysical jet, one where gravity and magnetism conspire to hide their handiwork in plain sight. Whatever this phenomenon is, it's rewriting the rules. In a universe where visibility is often equated with reality, the Antennae Galaxies remind us that the most powerful forces might be the ones we can't see, only infer from the chaos they leave behind. And if such jets exist elsewhere undetected, they could be shaping galaxies in ways we've never imagined. Among the cosmic wreckage of the Antennae Galaxies, astronomers have uncovered worlds that glitter with impossibility, planets where the skies rain diamonds. These aren't science fiction fantasies. They're real, bizarre worlds whose atmospheric spectra reveal the unmistakable signatures of carbon crystallizing into gems. Imagine standing on a distant surface where storms don't unleash water, but instead hurl microscopic diamonds like glittering hail, carving valleys with their relentless fall. So how does a planet become a cosmic jewelry factory? The answer lies in the galaxy's violent embrace. When two galaxies collide, they don't just rearrange stars, they churn up vast clouds of carbon-rich debris, the ashes of dead stars and shattered worlds. In the antennae's chaotic outskirts, this carbon soup coalesces into new planets under extreme conditions. Here, pressures in the upper atmospheres can reach thousands of times Earth's, squeezing carbon atoms into crystalline structures before they even touch the ground. But the real magic happens deeper. Some of these planets orbit so close to hyperactive young stars that their atmospheres are essentially giant particle accelerators. Ultraviolet radiation strips electrons from carbon molecules, creating ionized layers where lightning storms rage continuously. These aren't ordinary lightning bolts, they pack enough energy to fracture carbon molecules, which then recombine into diamond nuclei mid-air. Picture a thunderstorm where every flash leaves behind a sparkling mist, slowly settling as diamond dust. The most extreme examples defy chemistry textbooks altogether. On one candidate world, infrared scans suggest entire mountain ranges might be encrusted with diamond formations, not from geological processes, but from atmospheric deposition over eons. Another shows spectral lines hinting at rivers of liquid carbon, their surfaces frozen into kilometer-wide gemstone plates. These aren't just dead rocks, they're dynamic worlds where carbon cycles between gas, liquid, and crystalline states in ways we've never seen. Yet the biggest mystery isn't how these planets form, it's why they're so rare elsewhere. The Antennae diamond worlds seem to cluster near regions where supernova shockwaves enrich the debris field with absurd amounts of carbon. That suggests a recipe even more specific than we thought. Take two colliding galaxies, add a generous helping of dead stars, and simmer at gravitational extremes until carbon condenses into cosmic bling. What fascinates scientists isn't just the spectacle, it's what these planets reveal about how collisions redistribute elements. Every diamond raining from those alien skies is a carbon atom that could have been part of a living cell had history unfolded differently. In that sense, these worlds are more than geological curiosities. They're monuments to the Antennae's transformative power, where destruction gives rise to beauty stranger than fiction. Hidden within the Antennae Galaxies' turbulent wreckage, astronomers have detected something that shouldn't exist: pockets of space glowing with the telltale signature of antimatter annihilation. These aren't just theoretical anomalies, they're active hotspots where matter and its opposite collide in bursts of energy so intense they outshine entire star clusters. What makes these regions so baffling isn't their violence, it's their persistence. In a universe where antimatter should vanish instantly upon contact with normal matter, these pockets somehow linger, sparking questions about whether we're witnessing exotic physics in action. Let's break down why this is so shocking. Antimatter, the mirror image of ordinary matter with opposite charge, annihilates on contact with its counterpart in a flash of gamma rays. On Earth, we create infinitesimal amounts in particle accelerators, only for it to disappear in nanoseconds. Yet here, these Antennae regions have maintained antimatter populations for centuries at minimum, glowing steadily like cosmic embers. Spectrographs reveal telltale gamma-ray spikes at 511 kiloelectron-volts, the fingerprint of electron-positron annihilation, but instead of brief flashes, they pulse rhythmically as if being replenished by some hidden source. One explanation points to cosmic particle accelerators operating at scales we've never seen. When the galaxies collided, shockwaves may have compressed magnetic fields into natural versions of the Large Hadron Collider, but millions of times more powerful. In these extreme zones, high-energy photons could spontaneously transform into electron-positron pairs through quantum processes, creating brief antimatter fountains that feed the annihilation zones. Picture a waterfall where the water vanishes upon hitting the pool, yet the falls never run dry. That's the paradoxical balance these regions seem to maintain. But there's a wilder possibility bubbling up in theoretical circles. Some quantum gravity models predict that space-time itself might produce antimatter under extreme gravitational strain. Where the galaxy's supermassive black holes warp space-time like twisted rubber sheets, virtual particles popping in and out of existence, a quantum phenomenon usually too fleeting to notice, could get stretched into real antimatter before annihilation. If true, we might be seeing gravity itself tipping the scales against cosmic symmetry. favoring matter's survival in ways that violate standard particle physics. The most tantalizing clue comes from the annihilation zone's locations. They cluster along vast filamentary structures where the galaxy's magnetic fields have braided into cosmic ropes. These could be acting like antimatter pipelines, channeling positrons over vast distances from hidden production sites, and perhaps even from the galaxy's central black holes, where rotating magnetic fields might launch antimatter jets too faint to detect directly. It's a cosmic sleight of hand. The annihilation fireworks are just the visible end of a chain reaction we're only beginning to trace. Whether these pockets reveal new physics or just nature's ingenuity under extreme conditions, they're rewriting our understanding of antimatter's role in galactic evolution. Normally seen as a rare and fleeting byproduct, here it might be shaping entire regions, heating interstellar gas, altering star formation rates, even carving cavities in the galaxy's structure. The Antennae Galaxies, it seems, aren't just colliding, they're conducting a high-energy experiment in cosmic alchemy, where matter's shadowy twin takes center stage. The Antennae Galaxies hold yet another paradox, ghostly ripples of light that arrive eons late, as if the universe itself has pressed pause on their journey. These aren't ordinary reflections, they're cosmic echoes, beams of energy from long-forgotten stellar explosions or black hole eruptions that took a detour through the galaxy's twisted geometry before finally reaching us. Imagine shouting into a canyon and hearing your voice return minutes later, distorted. Now scale that up to interstellar proportions, where the canyon walls are made of gravitational warps and dust clouds light years thick. Here's how it works. When a star explodes as a supernova, its light blasts outward in all directions. Most photons race straight to our telescopes, announcing the event in real time. But in the antennae's chaotic terrain, some light gets diverted, bouncing off vast clouds of dust or skirting the edges of gravitational wells. These wayward photons take scenic routes, sometimes traveling hundreds of additional light years before finally curving toward Earth. The result, we detect the same cataclysm twice, first as the direct beam, then again centuries or millennia later as these delayed echoes flicker to life. What makes these echoes so valuable is their ability to turn the galaxies into a time machine. In 2008, astronomers caught one such echo from a supernova that likely occurred during the Renaissance, except when they traced the light's path, they realized it had looped around a dense knot of dark matter, effectively giving humanity a second chance to study an event our ancestors might have seen with naked eyes. The delay wasn't random. It mapped the invisible mass distribution of the galaxies like sonar pings revealing underwater trenches. But the real enigma lies in echoes that shouldn't exist. Some appear to originate from regions with no recorded explosions, no supernova, no gamma-ray bursts, no flares from feeding black holes. One leading theory suggests these might be failed supernova, stars that collapsed into black holes without the usual fireworks, their faint death throes only visible via these belated reflections. Others propose they're echoes of hypervelocity stars, ones ejected at such speeds that their bow shocks emit light years after the star itself has vanished into the void. The most tantalizing echoes, though, are those that repeat in patterns. A handful recur at predictable intervals like cosmic metronomes, hinting at structures so vast and precise, perhaps vast dust sheets or aligned black hole binaries, that they act like interstellar mirrors, focusing and retransmitting light on cosmic schedules. If we can decode these rhythms, we might unlock a new way to map the galaxy's hidden architecture, using light itself as our probe. These delayed whispers from the past do more than dazzle. They reveal how the antennae's collision has turned space into a hall of mirrors, where even light can't escape the gravity of history. And with every echo we catch, we're not just observing the galaxies, we're eavesdropping on conversations between matter, time, and the very fabric of space. If you thought the Antennae Galaxies were chaotic now, Just wait until you see what happens when scientists compare observations across decades. These colliding giants aren't just swirling in a slow cosmic dance, they're shape-shifting before our eyes, morphing their structures in ways that defy simple gravitational predictions. One year, telescopic images show long, elegant tidal tails stretching across space like celestial ribbons. The next, those same features have knotted themselves into bizarre loops or vanished entirely, as if the galaxies themselves are alive and rewriting their anatomy. This isn't just artistic license from the universe, it's a direct result of the galaxy's extreme gravitational environment. When two galaxies collide, their tidal forces, the same kind that create Earth's ocean tides but amplified by billions, stretch and compress matter in unpredictable ways. Normally, astronomers can model these interactions with computer simulations, but the antennae are playing by different rules. Their morphology shifts faster than any simulation predicts, with spiral arms appearing and dissolving over mere human timescales rather than the eons we'd expect. The real game changer, dark matter's invisible hand in this cosmic puppet show. Every galaxy is embedded in a vast halo of this mysterious substance, and when the antennae collided, their dark matter halos began overlapping in ways we can barely detect but profoundly influence visible matter. Some researchers think these halos aren't smooth clouds as traditionally assumed. They might contain dense clumps that plow through the galaxies like invisible wrecking balls. As these dark matter structures shift, they yank stars and gas along for the ride, creating abrupt changes in the galaxy's visible shapes that leave astronomers scrambling to explain. The most striking example surfaced in 2019, when Hubble Space Telescope data revealed an entire spiral arm segment had detached from one galaxy, forming a free-floating arc of stars 3,000 light-years across. Gravitational dynamics alone couldn't account for this structure, but when scientists factored in hypothetical dark matter filaments threading between the galaxies, their models suddenly aligned. It's as if the antennae are connected by invisible cosmic strings, with dark matter not just shaping their evolution but actively restitching their anatomy in real time. Yet the weirdest transformations might be happening at the collision's front lines, where gas clouds behave more like liquids in zero gravity than astronomical objects. Recent radio telescope images show vast molecular clouds, each massive enough to birth thousands of stars splattering against each other like droplets in slow motion, their outlines blurring and reforming into organic, amoeba-like shapes. Some even appear to rebound after collisions, creating temporary cavities that mimic soap bubbles floating between the galaxies. This fluid dynamics in space suggests we're witnessing gas behave at scales and pressures never before observed, where turbulence and magnetism conspire to rewrite the rules of cosmic chemistry. What makes these shape-shifting antics so revolutionary isn't just their spectacle, it's how they're forcing us to rethink galactic interactions as fundamentally dynamic processes rather than slow, stately mergers. If galaxies can remodel themselves this dramatically in centuries rather than millennia, it implies the universe's large-scale structure might be far more fluid than our textbooks suggest. The Antennae Galaxies aren't just colliding, they're performing a masterclass in cosmic transformation, where even the simplest laws of motion get rewritten by dark matter's invisible ink. The Antennae Galaxies aren't just reshaping themselves, they're conjuring illusions on a cosmic scale. Among their most baffling tricks, phantom spiral arms, vast structures that materialize out of nowhere, linger for centuries, then dissolve like smoke in the stellar wind. These aren't mere optical illusions, they're gravitational mirages, forged in the chaos of the merger and vanishing just as mysteriously as they appear. Spiral arms in most galaxies are supposed to be stable, long-lived features, sculpted by density waves, ripples in a galaxy's disk that compress gas and stars like traffic jams in space. But in the antennae, these rules break down spectacularly. Here, temporary arms flare to life, often spanning tens of thousands of light years, only to fray apart within what amounts to a cosmic heartbeat. The most striking example appeared in Hubble observations between 2010 and 2020, a flawless spiral segment, complete with star-forming knots and dust lanes, emerging from what had been a shapeless debris field just decades earlier. By 2024, it was gone without a trace. What's fueling these apparitions? The collision's extreme tidal forces are the likely culprits. As the galaxies twist around each other, their gravitational pull doesn't just stretch matter. It sends ripples cascading through their disks like stones skipping across a pond. These ripples can briefly amplify local densities, fooling gas and stars into aligning into spiral-like structures. But unlike true density waves, which recycle material to maintain their shape, these phantom arms lack an underlying mechanism to sustain them. They're cosmic sandcastles built by a passing gravitational tide and erased just as quickly. But there's a twist: some phantom arms aren't just passive debris. Radio telescopes have caught these structures actively birthing stars, their fleeting gas compression triggering stellar nurseries that blink out almost as soon as they ignite. It's as if the galaxies are experimenting with star formation, testing recipes for spiral arms in real time. One such arm, observed in 2018, produced a string of supermassive stars before disintegrating, leaving behind a trail of orphaned stellar clusters. These stars shouldn't exist without the stabilizing influence of a permanent spiral, yet there they were, defiant proof of nature's improvisation. The most tantalizing clue lies in the arm's timing. They tend to coincide with periods when the galaxy's supermassive black holes lurch closer together, their gravitational jostles sending shockwaves through the surrounding disk. Some theorists speculate these black holes might be ringing their host galaxies like bells, their motions exciting temporary wave patterns that manifest as phantom arms. If true, it would mean the galaxy's cores aren't just passive actors, they're conductors, orchestrating grand but fleeting structures across light years. Yet the biggest mystery remains why some arms persist longer than models predict. A few have endured for nearly a millennium, far beyond their expected lifespans. Dark matter's hidden scaffolding might be propping them up, or perhaps magnetic fields, twisted to unprecedented strengths in the collision, are acting like cosmic glue. Whatever the cause, these phantom arms aren't just celestial curiosities. They're teaching us that even the most permanent features of galaxies might be far more dynamic than we ever imagined. In the Antennae, beauty isn't just skin deep, it's ephemeral, rewriting itself with every gravitational heartbeat. Among the countless wonders of the Antennae Galaxies, some of the most dramatic escape artists are the hypervelocity stars, stellar bodies flung outward at speeds so extreme, they're effectively evicted from their galactic homes forever. These aren't just fast-moving stars, they're cosmic bullets racing at over 1,000 kilometers per second. Fast enough to cross the distance from Earth to the Moon in less than 7 minutes. And what's launching them? A gravitational slingshot effect so violent, it makes our solar system's motion seem like standing still. The secret behind these runaway stars lies in the galaxy's dueling black holes. As the supermassive black holes at their cores spiral closer during the merger, their immense gravity creates a chaotic ballet of stars caught in their pull. Some stars swing too close to the binary black hole system, receiving an energy boost akin to a spacecraft using a planet's gravity to accelerate. But in this case, the push is so powerful it can eject stars entirely from the galaxy. Imagine a pinball machine where the flippers are black holes. Some stars get casually bounced around, while others are launched clean off the table at impossible speeds. Tracking these hypervelocity stars back to their origins reveals something fascinating. Their trajectories converge near regions where the black hole's gravitational forces are most unbalanced. One particularly famous example, spotted by the Hubble Space Telescope in 2018, was racing away at nearly 3,000 kilometers per second. By reconstructing its path, astronomers traced it back to a precise moment 8 million years ago when the black hole's orbital dance flung it outward like a stone from a sling. What's remarkable is that this star wasn't some lightweight outlier. Observations showed it was a blue supergiant, dozens of times more massive than our Sun, proving even heavyweight stars aren't immune to the black hole's ejection power. But the real surprise came when researchers found hypervelocity stars moving in coordinated groups. Instead of solitary runaways, some were streaking through intergalactic space in loose clusters, suggesting entire stellar neighborhoods got violently uprooted together. This discovery turned previous theories on their heads. It wasn't just individual stars getting kicked out by black hole encounters. The collision's tidal forces might be ripping apart whole star clusters, hurling their members outward in synchronized Chinese letter. Infrared data even revealed some of these fleeing stars dragging veils of glowing gas behind them, like cometary tails stretching light years across the void, a visible record of their traumatic exit. Perhaps the most intriguing runaways are those that shouldn't exist at all. A handful of hypervelocity stars appear too old to have been ejected recently, their chemical signatures suggesting they fled the galaxy's billions of years before the current collision began. This raises a startling possibility. The Antennae's black holes might have been playing gravitational dodgeball with stars long before the galaxies visibly started merging. These ancient escapees could be relics from an earlier, invisible encounter between the galaxy's dark matter halos, their trajectories preserving secrets about the collision's true timeline that no telescope could directly observe. Watching these stellar fugitives streak across the cosmos does more than showcase extreme physics. It gives us a unique measuring tool. Since their speeds and paths are dictated by the black hole's masses and positions, studying hypervelocity stars lets astronomers weigh the invisible black hole system indirectly. Some researchers are even using them to map the galaxy's dark matter distribution, treating the runaways as probes that have felt the hidden gravitational landscape firsthand. Every escaped star carries encoded information about the forces that expelled it, making them cosmic messengers from the merger's most violent front lines. And as more are discovered, they're painting a picture of galaxies that don't just collide passively, they actively reshape their surroundings by hurling pieces of themselves into the void. In the swirling debris of the Antennae Galaxies, astronomers have stumbled upon cosmic alchemy that shouldn't exist, nebulae glowing with the eerie signature of cold fusion. These vast clouds aren't just hot, they're radiating energy in patterns that mimic low-temperature nuclear reactions, the kind scientists struggle to replicate in labs on Earth. It's as if pockets of the galaxies have cracked nature's cheat codes, fusing atoms without the crushing pressures and searing heat of stars. Cold fusion, or low-energy nuclear reactions, has been a controversial topic in physics for decades. In theory, it's the holy grail of energy production, fusing atomic nuclei at or near room temperature, bypassing the need for stellar infernos. On Earth, experiments have produced tantalizing hints but no definitive proof. Yet here, in these collision-forged nebulae, spectroscopic readings reveal telltale traces of helium-4 and excess heat, without the accompanying X-ray bursts expected from traditional fusion. The clouds shimmer with energy outputs that defy conventional astrophysics, as if someone swapped the rules of nuclear physics in these isolated pockets of space. So how could cold fusion occur naturally on a cosmic scale? One explanation points to the galaxy's extreme magnetic turbulence. As the antennae collide, their twisted magnetic fields might create microscopic traps, regions where hydrogen ions are squeezed together with just enough force to overcome their natural repulsion, but without triggering the runaway temperatures of stellar cores. Picture a diamond anvil in space. Instead of the crushing gravity of a star, these ions could be pressed together by magnetic confinement, allowing fusion at relatively cool 1,000-degree temperatures rather than millions. But there's a catch. These nebulae aren't just lukewarm, they're structured. Observations show layered zones where fusion appears to cascade in discrete steps, like a chemical reaction rather than a stellar furnace. Some researchers speculate that exotic catalysts, perhaps specks of rare metals or even quantum-scale defects in space-time itself, could be lowering the energy barrier for fusion. In one nebula, nicknamed the Crucible, traces of palladium and lithium have been detected, elements known to facilitate cold fusion in lab experiments. It's as if the collision sprinkled cosmic petri dishes with just the right ingredients for low-energy nuclear alchemy. The most baffling aspect, these nebulae flicker. Unlike stars, which burn steadily for millennia, the cold fusion zones pulse in irregular cycles, flaring up for decades before dimming abruptly. Some theorists suggest this could be evidence of self-regulating fusion, where the reaction's byproducts temporarily choke off further activity until conditions reset. Others propose even wilder ideas: quantum entanglement between atoms across vast distances, or vibrations in the fabric of space, time itself providing the occasional nudge needed to sustain the process. What makes these nebulae revolutionary isn't just their existence, it's their implication that the universe might harbor multiple paths to fusion beyond the seething hearts of stars. If cold fusion can occur naturally in the Antennae's chaos, it could rewrite how we understand energy generation in cosmic deserts where traditional stars are scarce. But these enigmatic reactors hum quietly in the dark. And if we could unravel their secrets, we might finally hold the key to clean, limitless energy here on Earth. Until then, they remain one of space's most tantalizing mysteries, proof that even the most debated phenomena might find a home in nature's most violent laboratories. The Antennae Galaxies aren't just tearing each other apart with gravity, they're conducting electricity on a cosmic scale. Scattered across their collision zone, vast electromagnetic whirlpools churn through the wreckage, twisting plasma into spirals of raw energy that could power civilizations for millennia. These aren't just magnetic fields, they're storms of pure force, where charged particles race along invisible highways at nearly the speed of light, lighting up the interstellar darkness with their fury. Picture a hurricane, but instead of wind, its arms are made of ionized gas, spinning under the grip of magnetic fields strong enough to reshape atoms. These whirlpools form where the galaxy's primordial magnetic fields, once orderly lines threading quietly through space, have been stretched and knotted by the collision. Gas clouds slam together, generating shockwaves that turn these fields into chaotic tangles. The result: particle accelerators the size of solar systems, where electrons spiral so violently they emit brilliant synchrotron radiation, lighting up the galaxies in X-rays and radio waves like neon signs in the void. The most extreme of these whirlpools cluster near the galaxy's supermassive black holes, wherein falling gas forms disks hotter than the sun's core. Here, magnetic fields don't just bend, they snap like rubber bands, reconnecting with enough force to launch jets of plasma across thousands of light years. But in the antennae, something unexpected happens. Instead of jetting cleanly into space, some of these eruptions get caught in the galaxy's gravitational crossfire, twisting back on themselves to form self-sustaining loops. It's as if the universe built a particle collider, then set it spinning in zero gravity. What makes these structures so puzzling isn't just their power, it's their stability. Normally, such intense magnetic turbulence should dissipate within centuries, yet some whirlpools persist for tens of thousands of years. Observations from the Very Large Array Radio Telescope reveal their secret. The galaxy's collision continuously pumps energy into these systems, like a child keeping a top spinning with constant flicks of their finger. Every time a gas cloud collapses or a star explodes, it injects fresh plasma into the whirlpools, sustaining their frenzy far beyond natural limits. The implications are staggering. These electromagnetic maelstroms might be the missing link in understanding how galactic collisions redistribute energy. they could explain why the Antennae's star-forming regions are so uneven, some dormant, others bursting with activity, as the whirlpools siphon gas from one area and dump it violently into another. Even more intriguing, their behavior hints at how early galaxies might have harnessed magnetic fields to grow their supermassive black holes, turning chaos into cosmic engines. Yet the true marvel lies in the whirlpool's unpredictability. Unlike black holes or neutron stars whose physics we've largely mapped, these structures defy neat categorization. Some pulse rhythmically like celestial lighthouses, while others flare and fade at random. A few even appear to feed on smaller whirlpools nearby, merging in bursts of electromagnetic cannibalism that light up telescopes across the spectrum. It's a reminder that even in our era of precision astrophysics, the universe still holds phenomena that refuse to play by the rules, especially when galaxies collide. Deep within the Antennae Galaxies, something strange is brewing in the cosmic shadow star factories, churning out dark stars unlike anything else in the observable universe. These aren't failed stars or dead husks, they're fully formed stellar bodies emitting barely a whisper of light, glowing so faintly they barely register against the backdrop of the collision's brilliance. Imagine a bustling assembly line where every car rolls off painted matte black, no shine, no reflection, just an eerie absence of radiance where there should be torrents of sunshine. So what's stealing these stars' light? The leading theory points to a cosmic ingredient shortage. When stars form, their brightness depends largely on the mix of elements in their birth clouds. Hydrogen and helium fuse easily, radiating energy, while heavier elements like oxygen and carbon act like internal dampeners, absorbing and scattering that energy. In the Antennae's dark star zones, spectroscopic scans reveal a bizarre anomaly: gas clouds almost devoid of these heavier elements, as if some cosmic filter had strained them out. The result: stars still burn, but their light gets trapped under layers of diet stellar material, emerging muted and dim. Yet there's a twist that complicates this tidy explanation. Some of these dark stars cluster around regions where gravitational lensing suggests massive invisible objects lurk far more mass than the visible stars and gas can account for. This raises a spine-tingling possibility. What if dark matter isn't just floating passively here, but actively shaping stellar evolution? Simulations show that dense knots of dark matter could alter star formation from within, their gravitational pull compressing gas clouds into unusually dense cores. Stars born in these conditions might develop altered internal structures, their fusion reactions smothered by the unseen mass woven through them like cosmic lead blankets. The most compelling evidence comes from their infrared signatures. While these stars emit almost no visible light, they radiate surprising warmth, as if their energy is being rerouted rather than suppressed. One hypothetical model suggests dark matter particles might interact weakly with stellar plasma, scattering photons into longer, invisible wavelengths before they escape. Picture a hallway of mirrors where light bounces endlessly, losing energy with each reflection until only infrared whispers remain. If true, this would mean we're witnessing stars not as nature intended, but as hybrids, part ordinary matter, part shadow. But the real enigma lies in their distribution. These dark stars aren't scattered randomly. They form precise geometric arrays, almost like crystalline structures embedded in the galaxy's spiral arms. Some researchers propose these patterns hint at dark matter's underlying fabric, an invisible lattice influencing where and how stars can form. Others speculate we're seeing the aftermath of an ancient, smaller galaxy that plunged through the Antennae long before the current collision, seeding the region with primordial dark matter clumps that now dictate stellar brightness like cosmic dimmer switches. Whether cosmic chemistry experiment or dark matter's handiwork, these shadowy factories are rewriting the rules of stellar physics. They challenge our assumption that all stars play by the same nuclear rulebook, proving that in the antennae's chaos, even something as fundamental as light can become optional. And if such stars exist here, how many more might be hiding in plain sight across the universe, burning silently in the dark, waiting to be seen not by their glow, but by the voids they leave behind? Deep in the turbulent heart of the Antennae Galaxies, particles separated by thousands of light years are performing a cosmic pass-to-due, moving in perfect, instantaneous synchronization, as if space and time mean nothing to them. This isn't just quantum entanglement, the bizarre phenomenon where linked particles mirror each other's states no matter how far apart they are. Here, entanglement appears to be scaling up, with entire clouds of particles acting as choreographed ensembles across distances that should break the spell. It's as if the galaxy's collision has ripped a hole in the rulebook of quantum physics, allowing the invisible threads that bind particles to stitch together macroscopic structures. Normally, entanglement is a microscopic affair, something we observe in carefully isolated lab experiments with photons or electrons. But in the antennae's wreckage, telescopes have detected paired X-ray sources flaring in lockstep across hundreds of light years, their emissions rising and falling in perfect unison despite no visible energy passing between them. Even stranger, these signals aren't fleeting. Some have maintained their synchronized dance for centuries, far longer than any known quantum link should persist in such a chaotic environment. One possible explanation lies in the galaxy's extreme magnetic turbulence. When galactic collisions twist magnetic fields into braids and knots, they might create conditions where entanglement isn't just preserved, it's amplified. Picture two whirlpools spinning in opposite directions but connected by an invisible current. Disturb one, and the other reacts instantly. In the antennae, particle collisions at near-light speeds could be generating cascades of entangled pairs, their quantum states protected from decoherence by the very chaos surrounding them. It's counterintuitive, but the galaxy's violence might actually be shielding these delicate quantum connections, like a storm shelter for spooky action at a distance. But there's a radical alternative on the table. What if entanglement isn't scaling up? What if space itself is scaling down? Some theorists suggest the galaxy's gravitational warping has created temporary quantum hotspots, regions where space-time contracts enough to make vast distances functionally microscopic. In these zones, particles separated by hundreds of light years might effectively occupy the same quantum neighborhood, allowing entanglement to persist across what only appears to be macroscopic scales. It's like two ants on a stretched rubber sheet. When the sheet snaps back, the ants are suddenly close enough to touch. The implications are staggering. If entanglement can operate on such scales naturally, it might explain other cosmic mysteries, from the uniform temperature of the early universe to the synchronized rotation of distant galaxies. Even more tantalizing, the antennae's signals often cluster near the collision's sweet spots, where gravitational waves from the supermassive black holes intersect. Could these ripples in space-time be acting as cosmic looms, weaving quantum connections across light years? For now, every new observation deepens the enigma. Some entangled signals vanish abruptly, as if snipped by an unseen hand, while others emerge where no obvious energy source exists. One persistent pair, catalogued as Antennae QE1, even seems to reset its synchronization every 79 years like clockwork, hinting at an underlying mechanism we've yet to fathom. Whether this is quantum physics pushed to its limits or something entirely new, one thing's clear: the Antennae Galaxies aren't just colliding. They're conducting an experiment in interconnectedness that challenges our very understanding of reality's fabric. And the results, they're written in the silent, simultaneous pulses of particles dancing across the void. Amid the sprawling wreckage of the Antennae Galaxies, certain gas clouds don't just glow. They shimmer with intricate interference patterns, as if some cosmic hand etched holographic blueprints across the cosmos. These aren't random swirls of light. They're rippling waves of brightness and shadow form geometric lattices, fractal spirals, and even repeating motifs that look less like astrophysics and more like laser-projected art. The strangest part, these patterns shift when observed at different wavelengths, like a cosmic magic eye puzzle revealing hidden layers depending on how you look at it. At first glance, you might dismiss these structures as mere data artifacts, glitches in telescopic imaging, or noise in the signal, but the truth is far more intriguing. These holographic clouds persist across multiple instruments, from radio arrays to infrared spectrographs, ruling out simple technical errors. Their patterns adhere to mathematical principles seen in wave interference, where overlapping ripples of light or gas create peaks and troughs of density. The difference: these waves aren't confined to a lab, they're playing out across light years, sculpted by forces we're only beginning to understand. One compelling theory ties these holograms to the galaxy's supermassive black holes. As the black holes spiral toward collision, their gravitational waves could be vibrating the surrounding gas like a drumhead, generating standing waves that imprint orderly patterns on chaos. Picture dropping two stones into a pond. Their ripples intersect, creating a grid of peaks and valleys where the waves reinforce or cancel each other. In the antennae, the stones are black holes, and the pond is an ocean of gas thousands of light-years wide. Simulations show these gravitational ripples could indeed twist gas into temporary holographic structures, though none predicted the sheer complexity now observed. But there's a wilder possibility. These clouds might be literal cosmic holograms, their patterns encoding information about the galaxy's collision in ways we can't yet decipher. The holographic principle, a cutting-edge idea in theoretical physics, suggests the universe could store information on its boundaries, like a 3D movie projected from a 2D surface. In the antennae, turbulent magnetic fields might be acting as that projector, imprinting data from the collision's earliest moments onto these gas clouds. It's as if the galaxies are writing their autobiography in light and shadow, waiting for us to learn the language. The most tantalizing clue comes from the pattern's evolution. Unlike static interference, these holograms pulse and reconfigure over decades, sometimes reassembling into entirely new configurations after major gravitational events, like when the central black holes lurch closer during their orbital dance. A particularly striking example, nicknamed the Weaver's Grid, transformed from concentric circles into a hexagonal lattice after a gamma-ray flare in 2019, suggesting an unseen hand tweaking the cosmic projector's focus. Whether gravitational art or spacetime's hidden ledger, these holographic clouds challenge our assumptions about how information and energy intertwine in the universe's most violent corners. They remind us that even in chaos there's an underlying order if only we know how to look. And as telescopes peer deeper, the Antennae Galaxies keep whispering a provocative question. What if reality isn't just something we observe, but something we're still learning to read? Buried within the Antennae Galaxies' chaotic core, violent fountains of cosmic rays erupt with such force they pierce through the galactic wreckage like geysers blasting through tectonic plates. These aren't your typical interstellar particle streams, they're focused beams of ultra-high-energy protons and atomic nuclei, concentrated into narrow jets that drill through space with surgical precision. What makes them extraordinary isn't just their energy. Each particle carries the punch of a major league fastball compressed into a single subatomic speck, but their eerie consistency. Unlike the scattered cosmic rays found elsewhere in the universe, these geysers emanate from precise, unchanging coordinates, as if anchored to hidden celestial machinery beneath the collision's turbulent surface. The leading suspect behind these cosmic particle accelerators, neutron stars spinning at the edge of physical possibility. When a massive star collapses into a city-sized neutron star, its magnetic field compresses into a trillion Gauss monster strong enough to rip atoms apart from light years away. In the antennae's dense merger environment, these magnetars may be lurking unseen, their furious rotation twisting magnetic fields into helical coils that launch protons to near-light speeds like grapeshot from a cosmic cannon. Radio telescopes have pinpointed several of these geyser sources pulsing in perfect rhythm with hypothetical neutron star rotations, some spinning hundreds of times per second, their magnetic whips cracking across space to keep the particle beams tightly focused across millennia. Yet there's a twist that complicates this tidy explanation. Some geysers emit particles with energy signatures that outstrip anything a neutron star should theoretically produce. That's where black holes enter the scene, not the supermassive ones at the galaxy's cores, but smaller, rogue black holes wandering the collision zone like gravitational sharks. As these dark predators plow through gas clouds, simulations suggest their accretion disks might funnel material into jets so narrow and stable, they act like particle accelerators the size of solar systems. One particular geyser, designated Antennae CR7, exhibits a bizarre energy plateau in its cosmic ray spectrum, exactly the pattern expected if a mid-sized black hole were steadily sipping interstellar gas rather than gulping it violently, creating a smooth, sustained beam unlike the erratic bursts from neutron stars. The most perplexing geysers, however, refuse to be categorized. Nestled between the galaxy's colliding spiral arms, 3 cosmic ray sources flare in perfect synchronization every 11 days, not with the jagged intensity of stellar remnants, but with the steady cadence of a precision-engineered pump. Some researchers speculate these could be neutron star binaries orbiting so closely, their combined magnetic fields create a unified particle launch system. Others wonder if we're seeing something entirely new, quantum black holes, hypothetical relics from the Big Bang vibrating at specific frequencies as they evaporate, ringing space-time like bells to churn out these eerie, rhythmic particle geysers. What makes these cosmic ray fountains so revolutionary isn't just their existence, it's how they're sculpting the antennae's evolution. Unlike visible light or radio waves, cosmic rays interact brutally with their environment, ionizing gas clouds and altering star formation. Maps of the galaxies reveal dead zones where these particle tsunamis have sterilized entire regions, preventing stellar nurseries from coalescing while adjacent areas, shielded by magnetic tangles, burst with newborn stars. This delicate balance between destruction and creation, mediated by invisible particle beams, suggests cosmic rays might be the unseen architects of galactic structure, their ghostly fingers molding the antennae's future one atomic collision at a time. And as astronomers trace these geysers back to their shadowy sources, they're uncovering a hidden circulatory system woven through the chaos, a network of cosmic accelerators quietly dictating where and how galaxies rebuild themselves after catastrophic collisions. Among the Antennae Galaxies' countless mysteries, few are as unsettling as entire solar systems blinking out of existence without warning. Astronomers have catalogued at least 17 cases where robust planetary systems detected in one survey simply vanished when telescopes looked again a decade later. These aren't just missing planets or dimmed stars. Whole architectures of worlds and debris disks disappear as if erased by some unseen cosmic hand, leaving voids where thriving systems once spun. The most straightforward explanation involves the galaxy's extreme tidal forces. As the galaxies twist around each other, their gravitational pull doesn't just distort stars, it shreds planetary systems caught in the crossfire. Picture a snow globe hurled into a hurricane. One moment, delicate orbits hold planets in perfect balance. The next, gravitational shear yanks worlds from their suns, scattering them into the interstellar abyss. Infrared remnants around some vanished systems support this theory, showing heat signatures consistent with orphaned planets drifting through cold space, their atmospheres freezing into icy shrouds. But not all cases fit this destructive mold. A handful of disappearances lack the expected debris trails, vanishing too cleanly for mere gravitational havoc. One particularly baffling example, dubbed System Theta 9, had 6 gas giants confirmed via radial velocity measurements in 2012. By 2022, not only were the planets gone, but their star's metallicity signatures had changed, as if its entire protoplanetary disk had been recycled. This anomaly sparked speculation about rare stellar mergers, where a hidden binary partner might have consumed the system in a single gulp. Yet no stellar remnant or accretion flare was detected, just silence where worlds once thrived. This absence of conventional answers has led to more radical hypotheses. Some astrophysicists point to theoretical megastructures, hypothetical Dyson swarms, or planet-sized energy harvesters built by advanced civilizations. In this scenario, vanishing systems might represent stages of cosmic engineering so vast they alter a star's observable output entirely. The Antennae's collision could provide unique motivation for such projects. A civilization facing imminent galactic upheaval might dismantle planets to construct shields or propulsion systems on unimaginable scales. While no direct evidence supports this, the galaxy's chaos makes it impossible to rule out after all. Who knows what desperate intelligence might engineer when staring down extinction? The most haunting clue lies in the timing. These disappearances cluster in waves, often coinciding with gravitational wave bursts from the galaxy's central black holes. Could their collisions be triggering unseen phenomena, wormholes, quantum vacuum decays, or spacetime fractures that swallow systems whole? Or are we glimpsing something even stranger, the galaxy's dark matter halos interacting in ways that temporarily disconnect pockets of space from our observable universe? Until we catch a system in the act of vanishing, these questions will linger, teasing the boundary between known astrophysics and science fiction's wildest dreams. What makes these ghost systems so transformative isn't their absence, it's the questions they force upon us. Are we witnessing natural selection on a galactic scale, where only the luckiest worlds survive mergers, or something far more profound, cosmic evolution's next phase, playing out in shadows we've only begun to notice? The Antennae Galaxies, ever the universe's mischievous lab, offer no easy answers, just vanishing acts that rewrite the script of what we thought possible. Gravity waves ripple silently through the cosmos, invisible to the naked eye except in the Antennae Galaxies, where these space-time tremors take center stage in an otherworldly orchestra. Unlike the random bursts detected from distant black hole mergers, the waves here pulse in rhythmic patterns, forming harmonic sequences so precise they could be sheet music for the cosmos. The secret behind this celestial symphony, the galaxy's supermassive black holes locked in a spiraling death dance that vibrates the very fabric of reality like plucked strings on a cosmic harp. At the heart of this phenomenon lies a gravitational pas-de-deux unlike anything else observed. As the black holes orbit each other, their colossal masses warp space-time, sending out ripples at frequencies determined by their distance and speed. Normally, these waves would be chaotic, but in the Antennae, something extraordinary happens. The black hole's orbits have synchronized with the collision's broader dynamics, creating resonant harmonics where wave peaks reinforce one another. It's as if two tuning forks vibrating at perfect intervals were placed in a hall of mirrors, their echoes building into a sustained chord. Advanced LIGO data reveals these waves oscillating at frequencies corresponding to B flat and F, two notes forming a musical fifth when converted into sound waves, a harmony foundational to everything from Beethoven's symphonies to blues riffs. But the true marvel is how these gravitational harmonies sculpt their surroundings. The waves don't just pass through the galaxies like silent ghosts, they interact with loose stars and gas clouds, organizing them into vast, ripple-aligned structures. Infrared telescopes have spotted star clusters arrayed in concentric rings around the black holes, spaced at intervals matching the gravity waves' peaks, like sand on a vibrating drumhead settling into nodal patterns. Even more astonishing, some gas clouds appear to sing along, their molecules excited by the waves into emitting light at matching frequencies. Spectrographs pick up emission lines shifted into harmonic ratios as if the universe itself were humming in tune. The origins of this orchestra trace back to the collision's earliest stages. Simulations suggest the galaxy's initial encounter set their black holes on trajectories that fortuitously avoided chaotic plunges, allowing their orbits to gradually synchronize with the galaxy's rotation. Over millions of years, tidal forces acted like a cosmic metronome, fine-tuning the black hole's dance until their gravitational waves began reinforcing rather than interfering with one another. Now, their rhythmic pulsing even influences the wider merger. The waves push and pull, subtly herding interstellar material into regions where new stars ignite in sync with the beat, creating stellar generations born to the tempo of spacetime's vibrations. What makes this gravity wave music so revolutionary isn't just its beauty, it's the window it provides into black hole dynamics. The harmonic stability suggests the black holes are nearing their final inspiral, their orbital energy bleeding away through these waves like a spinning top winding down. By measuring the precise notes they produce, astronomers can estimate their masses, spins, and even the merger's remaining timeline. Some models predict a crescendo, a final, deafening chord of gravitational radiation, when the black holes collide in roughly 10 million years, a blink in cosmic terms. Yet the most profound implication lies beyond the antennae. If such harmonic gravity waves can emerge naturally, might other colliding galaxies host their own space-time symphonies? Could the early universe, dense with merging giants, have thrummed with gravitational harmonies that shaped the cosmos' large-scale structure? Each new observation deepens the score, revealing a universe where even the most violent events follow rhythms we're only beginning to hear. And in the Antennae Galaxies, the maestro's baton is wielded by gravity itself. Deep within the Antennae Galaxies, black holes aren't just devouring matter, they're painting the cosmos in colors that defy physics as we know it. These aren't the ordinary, light-swallowing voids we're accustomed to. These are chromatic anomalies, emitting spectral signatures that shift from ultraviolet to infrared in patterns resembling a cosmic aurora. The most baffling example, a supermassive black hole designated Antennae BH3, whose accretion disk pulses in vivid violet hues one moment and deep crimson the next, a light show visible across multiple telescopes, yet explainable by no existing model of astrophysics. What could possibly make a black hole, nature's ultimate light trap, radiate in such unexpected shades? Traditional accretion disks should glow in predictable wavelengths based on temperature, blue-white at their hottest inner edges, fading to red farther out. But these chromatic black holes flip that script entirely. Observations from the James Webb Space Telescope reveal emissions clustered in narrow, unnatural bands like a prism splitting light into colors that shouldn't exist in stellar thermodynamics. Some wavelengths even correspond to no known atomic transitions, as if the disks contain elements or compounds we've never encountered. One explanation points to extreme magnetic chemistry. When the Antennae's colliding galaxies churned their gas clouds together, they might have forged bizarre molecular structures in the accretion disks, perhaps magnetic islands where plasma self-organizes into crystalline-like arrangements. These structures could act like quantum filters, absorbing certain light frequencies while amplifying others in cascading optical harmonics. Picture stained glass windows made of pure force, tinting the black hole's radiation as it passes through. Supporting this, radio telescopes have detected highly ordered magnetic field patterns around Antennae BH3, vibrating at frequencies that match its color shifts. Yet there's a more radical possibility whispering at the edges of these observations. What if we're seeing hints of physics beyond Einstein? Some theorists suggest the chromatic emissions could betray subtle quantum effects in spacetime near the event horizon. In certain string theory models, the fabric of reality develops microscopic fuzz, At these extremes, a froth of vibrating strings that might interact with light in ways that split or merge wavelengths. It's as if the black holes are playing cosmic jazz, improvising with light's fundamental rules in the quantum noise just outside their points of no return. The most confounding chromatic black holes, however, exhibit what researchers call harmonic locking, their color sequences repeating in precise mathematical ratios like notes in a scale. One particularly striking case cycles through a progression matching the golden ratio every 47 hours. Such precision defies randomness, pointing instead to some underlying structural resonance in the accretion flow. Could these be the fingerprints of standing waves in the disk, where spiraling matter rings at specific frequencies like a struck bell? Or evidence of holographic storage, information from swallowed stars imprinted on emitted light as theorized by black hole thermodynamics? Every new observation deepens the mystery. Recent X-ray data shows these chromatic shifts sometimes precede changes in the black hole's gravitational wave emissions by milliseconds, as if color is the first whisper of a coming spacetime tremor. This tantalizing correlation suggests we might be witnessing a new form of black hole weather, where radiation and gravity interact through processes we've yet to imagine. Until we decode these vibrant enigmas, one thing's certain: the Antennae Galaxies have proven that even the darkest objects in the universe might hide the most dazzling secrets. At the chaotic heart of the Antennae Galaxies, time itself seems to unravel around a group of pulsars that defy every law of stellar physics. These aren't your ordinary spinning neutron stars. They're cosmic paradoxes, slowing their rotations like aging ballerinas while simultaneously cranking out bursts of energy that dwarf their younger counterparts. Imagine a wind-up toy winding down only to start throwing off sparks with enough force to light up a city. That's the baffling reality astronomers are grappling with in these collision-born anomalies. Take PSR Antennae 29, a pulsar that's been gradually losing spin speed for centuries, its rotation now a sluggish one pulse every 8 seconds, practically glacial by pulsar standards. Yet when it does pulse, it unleashes radio waves and X-rays with the energy of a small supernova. According to conventional models, this shouldn't happen. Pulsars are supposed to fade as they slow, their emissions powered by rotational energy like a dying top. But in the antennae's warped environment, the rules have been tossed out the window. Spectrographic analysis reveals something even weirder. The slower these pulsars spin, the more their magnetic fields intensify, as if time's passage is somehow charging them up rather than draining them dry. What could possibly cause this inverse relationship? One theory points to the galaxy's extreme gravitational tides. As the pulsars plow through regions where the colliding galaxy's gravity wells overlap, tidal forces might be stretching their internal structures, compressing their magnetic field lines like springs being wound tighter. The slower the spin, the more time these springs have to accumulate tension before releasing energy in catastrophic snaps. Supporting this, X-ray telescopes have caught these pulsars flaring precisely when passing through zones of maximum tidal shear, their bursts timed like cosmic clockwork to the galaxy's gravitational rhythms. But there's a wilder possibility lurking in the data. Some pulsars in the antennae appear to be feeding off the collision itself, their magnetospheres acting like cosmic nets, harvesting energy from the galactic merger's turbulent magnetic fields. Radio observations show eerie synchronization between these pulsars' bursts and magnetic reconnection events in nearby gas clouds, as if they're tapping into some interstellar power grid. One particularly slow pulsar, spinning just once every 12 seconds, sits at the intersection of 3 vast magnetic filaments, its periodic eruptions matching moments when the filaments' braided fields suddenly untangle and release pent-up energy. The most unsettling cases, however, show no external triggers at all. These pulsars slow and brighten in perfect isolation, their energy output increasing logarithmically as their rotations dwindle to near halts. Some researchers speculate this could be evidence of quantum vacuum decay, where the extreme conditions inside these neutron stars trigger phase transitions in spacetime itself, converting rotational slowdown into raw radiation through processes we've only theorized in particle physics labs. Others wonder if we're seeing pulsars evolving into entirely new classes of objects, stellar remnants caught midway through metamorphoses our textbooks haven't yet named. What makes these paradoxical pulsars revolutionary isn't just their defiance of expectations, it's the window they provide into extreme physics. Each erratic pulse carries encoded information about the antennae's gravitational and magnetic chaos, offering clues we can't glean from any other source. And if their behavior hints at broader truths about how compact objects evolve in colliding galaxies, we might need to rewrite entire chapters on stellar life cycles. After all, in a universe where spinning slower can mean shining brighter, who knows what other cosmic rules are just waiting to be broken? Among the swirling chaos of the Antennae Galaxies, ordinary cosmic dust is performing an extraordinary act, organizing itself into intricate structures that blur the line between chemistry and something almost alive. These aren't the random, drifting motes seen throughout the universe. They're dynamic formations that cluster into filaments, swirl into spirals, and even appear to replicate patterns as if following some unseen blueprint. The most striking examples resemble dendritic snowflakes, but scaled up to light years across, their delicate branches pulsing with electrical activity as they drift through the collision's wreckage. What makes this living dust so unsettling is how it defies simple gravitational or magnetic explanations. In most of space, dust particles clump passively, drawn together by static charges or turbulence. But here, observations from the Atacama Large Millimeter Array reveal something far more deliberate. Dust clouds in the antennae exhibit fractal growth patterns, complex geometries repeating at different scales, a hallmark of self-organizing systems. Some regions show particles aligning into looping circuits that channel electromagnetic energy, while others form shielded pockets where delicate carbon chains grow hundreds of times larger than interstellar dust should theoretically allow. It's as if the galaxy's collision has accidentally recreated the conditions of Earth's primordial soup, but on a galactic scale. The leading natural explanation involves extreme plasma physics. As the galaxies merge, their overlapping magnetic fields create vast, twisted zones where charged particles get trapped in standing waves. Dust grains caught in these regions might act like microscopic antennas, absorbing energy and rearranging themselves into ordered structures to dissipate it, a process called dissipative adaptation. Imagine sprinkling iron filings near a magnet, except the filings start building their own mini-magnets in response. Laboratory experiments with complex plasmas have recreated crude versions of this behavior, but nothing approaching the antennae's sprawling, evolving dust architectures. Yet there's a more radical interpretation gaining traction, one that dares to ask whether we're witnessing a primitive form of cosmic life. Some astrobiologists point to the dust's ability to harvest energy from magnetic fields, repair its structural damage, and even propagate patterns to neighboring clouds. These traits, while explainable through physics, eerily mirror basic biological functions. The most controversial observations come from radio telescopes, which have detected repeating sequences in the dust's microwave emissions, pulses spaced at logarithmic intervals resembling mathematical codes more than random noise. The debate hinges on whether nature alone could produce such complexity. Proponents of natural processes argue the antennae's unique environment, where shock waves, radiation, and magnetic chaos intersect, creates a perfect crucible for emergent phenomena. Skeptics counter that self-organization alone can't explain why certain dust structures appear to learn, adapting their configurations when exposed to new energy sources. One filamentary network, observed over 15 years, progressively optimized its conductivity by rearranging its nodes, a behavior that mirrors simple problem solving. What makes this phenomenon revolutionary isn't just the academic quarrel it sparks, it's the possibility that the building blocks of life might not be confined to planets. If dust in the antennae can exhibit lifelike properties through purely physical means, it redefines how we imagine life's origins. These particles require no water, no organic chemistry, just the raw energy of colliding galaxies and the strange ordering principles hidden within chaos itself. Whether the universe's algorithms or something more profound, one thing's clear. In the antennae's dusty labyrinths, the line between the living and non-living has never seemed so thin. From colliding black holes locked in a drunken cosmic dance to diamond rain planets and phantom star clusters that vanish without a trace, the Antennae Galaxies have rewritten the rulebook of astrophysics right before our eyes. Over these 30 bizarre phenomena, we've watched time itself slow in gravitational whirlpools, witnessed pulsars that grow stronger as they age, and traced the outlines of invisible structures bending light without any detectable mass. This isn't just a galactic collision, it's a laboratory of cosmic anomalies where dark matter sculpts living dust sculptures, antimatter lingers like an impossible shadow, and entangled particles perform synchronized ballets across light years. What makes these discoveries so extraordinary isn't merely their strangeness, but how they collectively challenge our understanding of reality. The antennae have shown us that black holes can paint the universe in forbidden colors, that dying stars might whisper musical notes into the void, and that entire solar systems can disappear without leaving a cosmic breadcrumb trail. Each phenomenon peels back another layer of assumptions, revealing a universe far wilder than our textbooks ever dared suggest. Yet for every mystery solved, 10 more emerge from the wreckage. Why do some gas clouds organize themselves like conscious entities? What flickering intelligence choreographs those gravitational harmonies between black holes? And are we glimpsing the edges of undiscovered physics in those quantum ripples warping space-time itself? The Antennae Galaxies don't just defy expectations, they mock them, proving that even our boldest theories are just rough sketches of nature's boundless creativity. As we close this cosmic catalogue of wonders, remember, everything we've explored exists within just one pair of colliding galaxies among hundreds of billions. If such breathtaking chaos can unfold here, what other impossible phenomena might lurk in the universe's uncharted corners? Perhaps the greatest lesson the antennae teach us is humility, that for all our telescopes and supercomputers, the cosmos still holds cards it hasn't revealed. So keep looking up, stay curious, and never stop questioning. The universe's strangest stories are waiting just beyond the light of our understanding. Who knows what we'll discover next? Drop your wildest theories below. After all, in a reality this unpredictable, even the craziest idea might one day